Welcome to Scalecraft. In the last video, we learned that the load balancer sits in front of multiple servers and distributes incoming traffics. But here is the question no one talks about. How does it decide which server should get your request? Does it simply pick the first server, chooses a random one, or is there something much smarter happening behind the scenes? Believe it or not, choosing the wrong server can slow down your application, overload machines, or even bring down your entire upside down. Today, we will explore the algorithms that power modern load balancers, and by the end of this video, you will know exactly when each algorithm should be used. Let's continue our Amazon Flash Sale story. Amazon has 6 applications. Thousands of customers are continuously clicking buy now. Every second, the load balancer must answer one simple question: which server gets the request? Different load balancing algorithms answer this question differently. Let's start with the simplest one, the round robin. Suppose the servers are named A, B, and C. The requests arrive one after the another. The load balancer simply rotates through them. First request goes to A, second request to B, and third to C. Fourth goes to A, then B, and then C, and again and again. Think of it like distributing cards around a table. Everyone gets one turn, simple and fair, and incredibly fast. The computation is basically the current index modulus of number of servers. Since there is almost no computation involved, round robin is extremely efficient. But there is one huge problem. Not every request takes the same amount of time. Suppose the server A receive request that takes 10 seconds. Meanwhile, server B receive request that take 10 milliseconds. Round robin does not care. It simply keeps sending requests equally. Eventually, one server becomes overloaded while other almost sits idle. Clearly, we need something smarter. So we have weighted round robin. Now suppose Amazon upgrades one server. Instead of 3 equal servers, they have one powerful server, one medium server, and one small server. Should they treat all of them equal? Of course not. Weighted round robin assigns a weight to every server. Let's say we have server A with weight 3, then B with weight 2, and C with weight 1. Instead of rotating like A, B, C, with sequence becomes 3 times of A, 2 times of B, and 1 times C. So simple and easy to implement. But there is one still issue. What if today's strongest server suddenly become overloaded? Its weight does not change because the weights are manually configured. The algorithm still does not know what's happening right now. So instead of asking whose turn it is, let's ask something smarter. Which server is currently least busy? Suppose server A has 120 active users, server B has 15, and server C has 48. So which one should receive the request? Obviously server B, right? Least connections continuously tracks the number of active connections on every server and always chooses the one which is least busy. This works much better when request durations vary. For example, processing a payment may take several seconds. Loading a product page would only about milliseconds. Unlike round robin, least connections naturally balance this uneven workload. But the downside? Every incoming request requires checking all available servers, right? So if you have thousands of servers, this becomes more expensive than round robin. So, can we combine the strengths of both approaches? Absolutely. That's where we have weighted least connections. Suppose server A has twice the CPU of server B. Naturally, it should be allowed to handle more active connections. But instead of looking only at the active connections, weighted least connections compares connections divided by weight ratio, and the lowest one wins. This means larger servers can safely handle more users without being unfairly avoided. In fact, HAProxy, which is the most famous load balancer, that uses this strategy by default because it adapts to both server capacity and the current workload. Next we have the IP hash. Now Rahul logs into the Amazon. His shopping cart is already stored in server's B memory. Each request must continue reaching server B. Otherwise, his cart will disappear. IP hash solves this using a very simple data. Takes the Rahul IP address, calculates its hash, then compute the hash of IP modulus of number of servers. The results always point to the same server. Every request from Rahul reaches server B automatically. No sticky session required. Pretty clever, right? But here is the problem. Suppose a new server is added suddenly, right? This is something we talked in consistent hashing problem. Now almost every IP maps to different server. Session will break. Cache memory become useless. Even worse, if thousands of users share the same corporate IP, they all end up on the same server, creating a hotspot. There has to be a better solution, and that's where we talk about consistent hashing. You will get the link to the video in the top right. This is one of the most important concepts in distributed systems. So instead of hashing directly into the servers, consistent hashing places servers around a virtual ring. Every request is also mapped onto that ring. So when one server disappears, only the request that belong to the server moves somewhere else. Everything else stays exactly where they were. So let's compare. Suppose you have three cache servers A, B, and C, and let's say my server C failed. With IP hash, almost every request gets mapped because the number of servers changes. Now, with consistent hashing, only the request belonging to the failed server, that is server C, they will change. And how? We talked about that in the video above. Now that's why systems like Redis cluster, Cassandra, DynamoDB all rely on consistent hashing. It minimizes the cache misses during the scaling events. Next, we have the least response time. Sometimes active connections don't tell the whole story. Suppose server A, which has only 5 active users, but each request is taking 5 seconds. Server B, which have 20 users, yet responds in only 30 milliseconds. So which one is actually faster? Least response time combines both these matrices. So average response time and current active connections. The servers that both fast and lightly loaded wins. So this algorithm is ideal for applications where every millisecond matters. So for example, online gaming, financial trading, or the live streaming. Next, we have random with 2 choices. Now suppose your company has 10 servers. Checking all of them isn't difficult, right? But what if you have 10,000 servers? Scanning every server for every request suddenly becomes expensive. Here is the surprisingly brilliant solution. Pick any 2 random servers. Let's play on probability. Compare their active connections. Choose the better one. That's it. Believe it or not, this tiny trick performs remarkably close to least connections while requiring only constant time work. That's exactly why Envoy uses this strategy by default. Sometimes randomness is better or smarter than perfect calculation. Now, there is no universal winner. There is no universal winner. Each algorithm solves different problem. For example, round robin, perfect, simple, and it's used when all servers are identical and requests are simple. Weighted round robin, best when the servers have different hardware capacities. Next, least connections, ideal when request durations vary significantly. Weighted least connections, great for production systems with different server sizes. IP hash, useful for sticky sessions. Consistent hashing, essential for distributed cache systems. Least response time, best when latency is required, for example in trading. And lastly, we have random with 2 choices, excellent for every large clusters where speed matters. Now, choosing the right load balancing algorithm is just not about distributing traffic. It's about balancing fairness, speed, scalability, fault tolerance, and user experience. The wrong algorithm can overload servers. The right one can help your application scale to millions of users. In the next video, we will explore another essential system design component that sits right beside the load balancer. So, see you there. And until then, subscribe Scalecraft.